Hello everyone, welcome to my channel Physics Tricks. So let us study about magnetic field on the axis of current carrying circular coil. So this is the current carrying circular coil which carries the current, if you see, from this direction in the anti-clockwise manner, and if you see from this direction in the clockwise manner, right? So the clockwise and anti-clockwise will change according to what is called as the if you change the location. So at this point, as you can see, the current is flowing out of the plane, right? Current is coming out of the plane. So as the current is flowing out of the plane, we'll consider the smallest element possible, and that smallest element is ideal bar supposed to be. Now, due to the smallest element at point P, we want what is the magnetic field. Now, to find the magnetic field at point P, we have to firstly draw what is called as the position vector. So this position vector we have, this dl's position vector at point P is, let us consider R. What is the radius of this circular coil? Let us consider the radius is capital R. The distance from center to point P is D. Now as you can see, R we have is equal to root of R squared plus D squared. R squared plus D squared. So this is perpendicular, we have R squared plus D squared. Now if I consider this angle as theta, and if I want what is the magnetic field due to this smallest element possible at point P, to find the direction, I'll firstly take what is called as the out of the plane current carrying conductor, and if I want what is called as the magnetic field at a position vector R, and that point P is supposed to be. If I want to at point P, so what you have to do is you have to stretch the thumb in the direction of the current that is out of the plane, and just see the direction of the palm. That direction of the palm at point P is pointing in this direction, right? In this direction. So you can draw actually the direction of magnetic field at point P is in this way, which is perpendicular to the position vector, right? Which is perpendicular to the position vector. Likewise over here, if I want at point P, so what you have to do is that the current is flowing out of the plane, right? Out of the plane, and at point P, if you see, it is going in that way, that is perpendicular to point P, the position vector R. So this is the what is called as the magnetic field dB. So this is 90 degree we have, and what is this angle then? It is 90 minus theta. Okay, right, now 180 total, so 180 minus 90 minus theta will become 90 minus theta. Okay, now likewise for every real element there is another real element symmetrical which is going inside, and if I want what is the magnetic field due to this current carrying element at point P, so you can see that magnetic field will be at certain angle downward, isn't it? At certain angle downward. So that I will draw in this manner. So as you can see over here, now this angle is theta because it is symmetrical, then it is 90 we have, and this must be 90 minus theta. Okay, so for every dB element there is another dB element, and we can have the two components of it. One is dB cos theta and other one is dB sin theta. And as you can see, for every dB element, as dB sin theta and dB cos theta is present, dB sin theta will get added, but dB cos theta will get cancelled out, and that is the reason dB net we can write, and that is dB sin theta. So I hope this is clear, right? It is the only dB sin theta component which stays over here, and dB cos theta will get cancelled out. Now see, if you want dB, if you wanted to write dB, you have to use what is called as the Biot-Savart law. What is Biot-Savart law? It gives the direction and magnitude of the magnetic field at point P. Now what is that Biot-Savart law? It is mu naught I dl divided by 4 pi r squared. So if I just write over here dB as mu naught I dl divided by 4 pi r squared is r, whole squared into sine theta we have. Now, what is r squared over here? Just now we have seen that is capital R square plus small r squared. So, mu naught I divided by 4 pi r squared into what is sine theta? Sine theta we have is capital R by small r into dl we have. So, dB net magnetic field at point P is mu naught I capital R divided by, this is 4 pi r cube into dl. Now just integrate it. For 0 length, let us consider magnetic field as 0 Tesla. For entire 2 pi r length, what is the magnetic field? That is what we have to calculate. So over here, if you just differentiate this, you will get integrate this, you will get B net, and which is equal to mu naught I capital R divided by 4 pi small r cube into what is dl over here? dl over here we have, and that is dl integration is L, and upper limit we put, you will get 2 pi into capital R. So this 2 pi, this will become 2. So what is the net magnetic field we have? And that is mu naught I r squared divided by 2 into r cube. So which is equal to mu naught I r squared divided by 2 into, what is r over here? It is r square plus d square whole raised to 1 by 2. So it will become 3 by 2. So the net magnetic field we have, is mu naught I r squared divided by twice of r squared plus d squared whole raised to 3 by 2. So I hope this is clear. So this is the magnetic field on the axis of current carrying circular coil. Now to validate this, let T is equal to 0 meter. Then what will happen? The net magnetic field will get at the center. And what is that net magnetic field then? Mu naught I r squared divided by 2 times r squared plus 0 squared whole raised to 3 by 2. And as you can see, you will get, this is mu naught I r squared divided by 2 times r cube. So this will get cancelled, and we'll get mu naught I divided by 2r. So this is the magnetic field at the center of the net magnetic field at the center of the current carrying circular coil, mu naught I divided by 2r. Net magnetic field at the center of current carrying circular coil. So I hope this is clear. It's very simple, right? And now if you want, what is the magnetic field position, right? What is the position where the net magnetic field is maximum? Now see, for that, the net magnetic field we have. So I'll just write over here. What is the position? What is the position where net magnetic field maximum? And as you can see, the net magnetic field we have, and that is equal to mu naught I divided by mu naught I r squared divided by 2 times r cube. Indicates what? Indicates as we increase the r, net magnetic field will decrease, right? Net magnetic field will decrease, and this will be maximum when r will have the minimum value, and r will have the minimum value when d is equal to 0, as you can see over here. See, what is r? R is the smallest element possible, no? This is d square plus r square, whole root is r. So r will have the minimum value when d is equal to 0. So r will have the minimum value when d is equal to 0, indicates B net will be maximum at the center. at the center of the current carrying circular coil. And if you just draw the graph between the magnetic field and the position, between the magnetic field and the position, the graph you will get is somewhat like this. So it will have its maximum value at the center, that means at the origin, and it will have the minimum value at the both the infinite positions, whether it is minus infinite or the plus infinite. And the maximum value we have, is mu naught I divided by 2R. This is the maximum value possible for the current carrying circular coil at its center. Okay. So I hope this is clear. Now, if anyone has any doubt, they can always comment in the comment box. I'll try to reply to your comment as soon as possible. Thank you so much.